So I can say that it is a very dedicated and talented student. So he basically for many years was a cornerstone of our group. And I just not wasting any more time on this introduction, will just invite Rich to present his work. Then, of course, it will be discussion and questions from the public, right? And then it will be a closed session when Rich will address questions from the committee. So this is the procedure. Then will be committee deliberations, and we will announce our decision afterwards. All right. So Rich, your turn.
All right. Thanks, Alex, for that really nice introduction. Okay, so good morning, everybody. Today I'm going to be presenting my dissertation entitled Molecular Modeling of Adsorption of Simple and Complex Fluids on Nanoporous Materials for Characterization. So I'm going to begin with a little bit of overview. I'll start with some background on nanoporous materials and adsorption characterization. And then I'll delve directly into my work, which is split into two main parts. In the first part of my presentation, I'm going to be talking about the adsorption of simple fluids on porous materials. And in the second part, I'll talk about complex fluids, namely polymer adsorption. I'll then wrap up everything with a brief summary. So, nanoporous materials exist all around us, and though many people might not know this, they affect us every day. Several classes in nanoporous materials are zeolites, such as are used in catalysis and other kinds of things. Silica here, so this guy's a silica packet you find used in your clothes and stuff. They suck in moisture from stuff and keep them dry. Silica is also found in sunscreen and also in fertilizer and all other stuff like that. Another class of nanoporous materials are carbons. So carbons are found in your water filters, in charcoal, and this is actually a picture of cat litter, but you can't see it very well. And then a fourth class are polymers. So the nanoporous materials are divided roughly into two groups. First are they're classified by their pore size. So mesoporous materials are those which have pores which are between 2 and 50 nanometers. Below this scale are microporous materials that are less than 2 nanometers. And some materials that have pores which are even smaller than 1 nanometer are called ultramicroporous materials. So when characterizing nanoporous materials, there are four main things that we're looking for. We want to know the pore size distribution of the material, the surface area and the total volume that the material has, the geometry of its pores, and the connectivity of the pores to one another. One of the main ways that we can do this characterization is with the process of adsorption. So adsorption is the process by which molecules called adsorbate stick to the surface of a material called the adsorbent. There are two different types of adsorption that are characterized by the way that the adsorbate interacts with the adsorbent. In chemisorption, we have chemical bonds that are formed between the adsorbate molecule and the adsorbent. And in physisorption, we have dispersion or van der Waals forces, which are doing sticking. My work all focuses on physisorption. So how do we measure physisorption? There are a couple different ways, and these are the two most common. The first is called gravimetric adsorption. In gravimetric adsorption, you have a cylinder of your adsorptive gas, and it's connected to a box. And inside this box, there's a spring attached to a cup which holds your sample in it. And what the cup is doing, and what the spring is doing, is moving up and down, and it's weighing your sample as the adsorptive is pumped in. And what we do is we look for the weight at which the weight stops fluctuating. That's the equilibrium amount. The other method is called volumetric adsorption. In volumetric adsorption, we have the same cylinder that's attached instead of to the whole box, it's attached to just a sample holder that's inside a temperature-controlled bath. And here we test the pressure inside the sample to see how we repeatedly expose the sample to little doses of the gas until the pressure doesn't change. And the pressure at which it doesn't change is the equilibrium. And that's the equilibrium uptake at one pressure. So in the course of my talk, I'm going to be talking about adsorption, physisorption of several different types of fluids, roughly distinguished by what we call simple or complex. Simple fluids are monoatomic or very lightly polyatomic, such as argon, water, krypton, CO2, and nitrogen. And complex fluids I'm restricting to just polymers for this talk. So one of the main ways that we quantify adsorption is through something called an adsorption isotherm. An adsorption isotherm, and these are several different types shown here, is a graph of the amount adsorbed as a function of often relative pressure. So this is basically the uptake of your adsorptive at a certain pressure. And we do this over a wide relative pressure range to get our full adsorption isotherm. And adsorption isotherms can have very different shapes based on all the characteristics of your material, and this is where we derive all that useful information from. Skipping those. So adsorption hysteresis is a special phenomenon which occurs in mesoporous materials. And I've done a lot of work specifically on characterizing hysteresis. Hysteresis occurs when the reverse process of adsorption, called desorption, doesn't follow the same path as the adsorption branch. And we can, hysteresis curves vary greatly also based on the specifics of your material, and can tell us a lot about the pore structure. So, with that introduction, I can start talking about the first part of my research on simple fluids. In the first chapter of my dissertation, I looked at a special type of adsorption and desorption isotherm called a scanning isotherm. So what's a scanning isotherm? Scanning isotherms, so this is our main hysteresis fluid. A scanning isotherm occurs when, if we go up on the adsorption branch, and all of a sudden we decide we want to go backwards and desorb instead of going all the way to capillary condensation, we get this additional curve which is inside the main hysteresis loop. It goes from the adsorption curve all the way to the desorption curve. And we can do the same thing from the desorption curve back up to the adsorption curve. So scanning isotherms like this, as I said before, can tell us a lot about the pore structure. Two main types of scanning isotherms are found in either regular materials, such as SPA15, or highly disordered materials. In fairly regular pore size or pore structure materials, we have these closed loops that form inside the hysteresis loop. And for disordered materials, we have a very different behavior, wherein if we're on an desorption scanning curve, it goes to the closure point of hysteresis, and an adsorption scanning curve goes to the other closure of the hysteresis loop. Okay, so in order to do our analysis, we have to learn a little bit of anatomy about isotherms. So the boundary hysteresis curve is shown here in black. This is the relative pressure, which I denote by the Greek letter chi, and this is the amount adsorbed at each pressure. Our primary adsorption isotherm is called V+, and I denote the primary desorption by V-. We can think of the adsorption and desorption boundary curves as being composed of fractions of two reference curves. The first one being the surface reference isotherm. The surface reference isotherm you can think of as the adsorption that would occur on a flat, non-porous surface. And the other curve is our condensed liquid bulk isotherm. So we can also something called the fraction of unfilled pores, which is basically the inverse of our adsorption isotherm. So it's the difference between our adsorption isotherm and the surface isotherm normalized by the total difference between those two curves. And when we apply this equation to both curves, we get something that looks like an inverse hysteresis loop. And so the main part of this entire chapter is being able to describe theoretically what these two curves look like for both the boundary hysteresis curve and also the scanning curves. And this differs based on porous material. So we can apply the same analysis to a scanning curve. Again, we have a scanning desorption isotherm which starts at pressure chi A and leads to somewhere on the desorption curve. And then we have an adsorption scanning curve which starts at a pressure chi D on the boundary desorption curve and stops somewhere under the boundary adsorption curve. And again, these can be described as fractions of unfilled pores as well. So to begin, we need to first talk very, very briefly about something called the theory of independent domains. So in a nutshell, the theory of independent domains says that the pore space in a material can be divided into subspaces or individual domains of pores in which the capillary condensation, which is that step, or the capillary evaporation, which is that step, can be treated as occurring independently of one another. In the very simplest of approximations, we can say that at any one particular pressure on the adsorption or the desorption curve, this pressure corresponds to the capillary condensation or evaporation of one pore size. So here we have a pressure chi A at which we're desorbing, and the pressure at which this is adsorbing corresponds to a single pore size. I can think of what I call this guy, D2. And similarly, we also have another pore which is smaller called D1, which evaporates later than D2. So at the next level of complexity is something called pore blocking. So this is our first attempt at looking at networks of pores, but on a very small scale. So in the pore blocking mechanism, the filling of adsorption or the filling of the pore space and the emptying of the pore space are slightly correlated to one another. First, upon filling, we have control. So if we imagine that we have one pore which is connected to two pores which are smaller than the main pore, the filling of this tiny pore space is going to be controlled by the radius, or by the diameter of the bigger pore. However, on desorption, the evaporation from this big pore is going to be delayed because these smaller necks have to evaporate at a much lower pressure than the big pore would. This leads to a delay in your overall evaporation from your pore system. So the first result of this particular piece of work was developing a theory for the fraction of unfilled pores in these partially correlated systems. And what we developed was this theoretical model called the partial correlation model, which allows us to better approximate the scanning curves of partially correlated materials. Okay, so the partial correlation model can also be used as a probe for porous materials which are disordered. So this picture here is a schematic of Vicor glass, which is a highly disordered porous material. And as you can see, these are adsorption scanning curves on this material. Everything works very well in the partial correlation model. However, on desorption, we see that the model fails pretty spectacularly. And the reason for this is that we don't have these independent domains for pores. They're all interconnected. And so, in order for us to accurately capture network effects, we have to introduce something called percolation theory. So in percolation theory, we abandon the concept of independent domains. And we instead set up a network of interconnected and interacting pores. To account for pore blocking and for these network effects, we introduced into our equation for the fraction of unfilled pores probability factor alpha. We have two different ways that I looked at how to calculate alpha. The first is by using a lattice approximation. So in this particular lattice, we have the nodes which denote the pores, and the lines between them are the necks between the pores. We say that any pore is connected to 3 other pores, and you can't have loops back to the pore where you started. What this allows us to do is develop an analytical equation for alpha in this case, based on probability and the connectivity of the pores to one another. The other way is to use a Monte Carlo simulation. So, very briefly, I just wanted to talk about the percolation threshold because it's very central to this piece. So, percolation, this is our, if we take this as a model of our pore system, we have pores, which are these spherical bits, and then they're also all connected to necks, which make the lattice connect to each other. The X's denote blocked pores, which are through which the fluid cannot desorb. And what we wish to know is the probability that this pore I can desorb based on the fraction of these necks which are blocked or unblocked. Percolation occurs when during the first instance in when there is a direct line to the surface, to the external surface of the material. In partially saturated networks, so like in the case we have a scanning curve, your pore system is not entirely filled. So the probability that you're going to have a percolating network is a lot higher. And you can desorb at lower pressures. So what I did was to look at both the beta lattice approximation and Monte Carlo simulations to calculate the alpha factor and the fraction of unfilled pores as a function of these metastable or unblocked necks. And with both of those approximations, I was able to accurately describe the desorption from these more disordered networks. A byproduct of all of these fractions of unfilled pores is that we can also describe pore size distributions of these materials. So this is a graph of all of these are 4 different samples. This is the pore size as a function of the differential volume. So for these 4 samples, we had pores of different sizes from 10 up to 40 nanometers, and they're given by these pore size distributions here, which very accurately reproduce what was known experimentally. We also can describe the fraction of the size fraction of the pore size distribution of the necks between the pores, and that'll land somewhere around one nanometer. So, in summary of the first chapter of my dissertation, I looked at several different models for describing the pore structure of materials using analytical and computational models, uncorrelated, partially correlated, and pore network materials. This piece of my dissertation was my first author paper, which was published in 2013. Okay, so I next looked at the characterization of micromesoporous carbon materials by high-pressure CO2 and argon absorption. So in this section of my dissertation, I used a different computational technique to look at a very special case of absorption in specific materials called micromesoporous carbons. Micromesoporous carbons are shown. So this is a picture of one particular micromesoporous carbon called CMK3. So typically, micromesoporous carbons are analyzed with either argon or nitrogen absorption at cryogenic temperatures, which means 77 to 87 Kelvin, which is very cold. And these from these adsorption isotherms, we can derive a bunch of information about pore size of our material using some methods which I'm about to talk to you about. However, we run into a problem in the very low relative pressure range in that we lose some of our experimental accuracy in the absence of very high pressure, very low pressure turbomolecular pumps. So what researchers have done in the past 20 or so years is started to look at using additional analysis gases such as carbon dioxide. And what they were doing up until very recently was just looking in the relative pressure range down here to look at the adsorption of CO2 in these really, really tiny micropores. Because carbon dioxide can, because it's done at a much higher relative pressure, or higher temperature, it can penetrate into the smallest micropores of your material a lot faster and a lot more accurately than argon and nitrogen can. And what I did in this portion of my dissertation was to extend the relative pressure range of our CO2 adsorption all the way up to the saturation pressure of CO2. And what this allows us to do is to compare the entire isotherm of nitrogen and argon to CO2 so that we can also capture mesoporous PET as well as the micropores. In order to do this, we need to use something called high pressure gas adsorption. And there are only very few instruments that are capable of doing this. So, for example, in this particular instrument, which was used for the CO2 analysis, you can reach pressures of over 35 bar. For reference, we're at atmospheric pressure. This is approximately 1 bar, so this is very high pressure. So here are examples of adsorption isotherms on CMK3 materials. We looked at 3 different samples of CMK3 that differ only in their method of synthesis. We have argon adsorption in blue, nitrogen adsorption in red, and CO2 adsorption in black. And I just want to point out a couple of things about each of these. So in all of the cases, we have a very pronounced adsorption need in argon and nitrogen, which indicates that we have a lot of microporosity in our system. Also, all of the samples have one primary mesopore, which can be seen by this hysteresis loop that occurs in each one. However, each of the samples has a hysteresis loop which occurs at a different different relative pressure, which indicates that we have different pore sizes of each. For the CMK3A and B samples, we also have a secondary hysteresis loop and a condensation step, which occurs because of larger, either larger mesopores or possibly adsorption on the external surface of the material. The other thing that I want to point out is that the CO2 adsorption in each case has approximately the same shape. They have a very spread out capillary condensation step relative to nitrogen and argon. And also, the adsorption and desorption from CO2 is completely reversible at this temperature. This occurs because we're very close to the critical temperature of CO2. So in order to study the adsorption of argon and CO2 on these carbon materials, we use a computational method called density functional theory. So in a nutshell, density functional theory relies on finding the equilibrium density profile, so shown here, either the green or the red, inside a model pore. This is accomplished by minimizing our drain potential, which is a function of the fluid and the solid density across your pore. We take the first derivative in the fluid density, set it equal to 0, and we get our equilibrium density profiles. We have to do this once for every pressure at which we wish to do a calculation, and so we have to string together a bunch of these calculations to get one adsorption isotherm. We use 2 different solid models, 2 different density functional theories in our modeling. The first is called non-local density the quantum-solid density functional theory was developed in our group. So the main difference between non-local and quantum-solid density functional theory has to do with the solid-fluid interactions in your pore. So in non-local density functional theory, the fluid interacts with a solid potential, which is emitted from the pore. In quantum-solid density functional theory, and also this density profile is constant in space, so it's all one density. In quantum-solid density functional theory, we have a variable density along the pore wall, and this allows us to account in a certain way for the roughness that's inherent in a lot of these quartz carbons. So if we take a bunch of these theoretically calculated isotherms and we put them together in something called a density functional theory kernel, this kernel is used to analyze a single absorption isotherm, such as this one shown here, by fitting something called the integral absorption equation. And so this is our experimental isotherm, which is the convolution of our kernel and the pore size distribution. So when we put these two guys together, it spits out the pore size distribution. And in this case, we have pores around 5 nanometers and something else. So one of the main aspects of this part of the work was developing the kernels. And so for the particular kernels which I'm going to talk about, they have two different pore geometries. For pores which are smaller than 2 nanometers, we use a slit-shaped pore model. And for pores which are larger than 2 nanometers, we use a cylinder. And this is because we're trying to fit best these CMK3 materials, which are roughly cylindrical in their main mesopores, but have slit micropores approximately. We used a Leonard-Jones parameterization to take care of both the solid fluid and the fluid-fluid interactions in CO2 and carbon, and also argon and carbon. And one thing that's important to note is, of course, that CO2 is not a Leonard-Jones sphere by any stretch of the imagination. However, we can approximate the CO2 molecule by a Leonard-Jones sphere if we correctly parameterize our model. So, in summary, I created many different argon and CO2 absorption kernels during the course of my dissertation, which encompassed several different geometries, from slit to cylindrical to spherical pores. And these have all been, well, actually, only the argon so far, but hopefully the CO2 will soon be implemented into Quantichrome's absorption characterization software, which is used by many people worldwide. Okay, so this is an example of a pore size distribution that we get applying argon, nitrogen, and CO2 absorption kernels to our absorption isotherms that we showed before. As you can see, our pore size distribution in the mesopore range agrees really, really well across all three analysis gases, which was a very fortuitous thing, which I can talk about later. Also, we have a slight difference that occurs in the micropore range. And this, again, we think is because CO2 is capable of penetrating into smaller micropores than argon and nitrogen, and so it can resolve pores which are a lot smaller. We also looked at just the main mesopore size for each of our three samples, and as we expected, we can distinguish the pore size of each one, going from the small one, which is the CMK3A, to the large one, which is the C. Also, we can look at the cumulative pore size distribution, which is, so along this axis we have the pore width, and this is the total volume at one pore width. So as we progress along along this graph, we're adding the total amount absorbed at each step. So we have a first uptake that occurs in your micropores, and then the second uptake that occurs in your mesopores. And we have really, really excellent agreement across all the analysis gases for this. this is the second part of my of this chapter. This was published in two different publications, so the stuff on argon was actually my first publication, which was not a first author, but to which I contributed, and the second one is going to be published hopefully soon. We're going to submit very soon. So in this particular section, I developed novel QSDFT kernels to analyze CO2 and argon absorption isotherm over a very wide pressure range. And I showed that CO2 isotherms in mesoporous carbons lack hysteresis. Also, I showed that the DFT pore size distributions that we get from CO2 are in good agreement with argon and nitrogen. Okay, so that is the first half of my research on simple fluids. In the second half of my dissertation, I took what I learned from the simple fluids and applied them to a special case of a complex fluid, namely polymer absorption. So in the first chapter of this section, I studied the critical conditions of polymer absorption on surfaces. So here is a picture of a polymer which is tethered by one end to a flat surface. And depending on the solvent conditions or the temperature, you have different geometries of your polymer. So when the solvent is a good solvent, the polymer is going to want to stay in the solvent as opposed to staying on your surface. And so we call this weakly absorbed. The polymer adopts a conformation like this, which is what we call the mushroom conformation. In the opposite case, such as shown here, when we have a really poor solvent, the chain is going to want to escape the solvent, and so it flattens itself against your absorbing surface, and this is called strong absorption. And there is a case in which your solvent conditions are such that the chain is equally likely to be absorbed or not absorbed. And this is called the critical point of absorption, the CPA. And so in order to study the CPA, we introduced something called the incremental chemical potential criterion. So the incremental chemical potential can be thought of as the work necessary to add or remove segments of our chain from the end of the chain. And it's related to the free energy of the chain, as shown in this equation. The critical conditions of polymer absorption correspond to the balancing between the different effects on the chain, both enthalpic and entropic. And it implies that we have the quality of our incremental chemical potential for both adsorbed and free chains. So this is our new critical condition that we described thermodynamically. In all of this section of the work, I use the same coarse-grained model. Our beads, which are shown in the black circles here, are represented by Leonard-Jones spheres, which are connected by harmonic bonds. And beads which are not directly adjacent to one another interact via Leonard-Jones potential. In all of my modeling, I do not include an explicit solvent. And so in order to account for the absorption interactions with the surfaces, I have to introduce something called introduce an absorption potential along the surface. And for simplicity, we use just a simple square ball. Our absorption potential is called U. So to calculate the incremental chemical potential, we use something called the incremental gauge cell method, which is a Monte Carlo method that was developed in our group and expanded upon by previous PhD student in our group, Chris Rasmussen. So in the incremental gauge cell method, we have our simulation cell, which holds our polymer, and it's in thermal equilibrium with a gauge cell of free beads, which can be removed or inserted to the end of the chain. The total number of molecules in both cells is constant, as well as the constant temperature and constant volume. And so at equilibrium, we're minimizing the Helmholtz free energy. And to calculate the incremental chemical potential, we actually don't need to know what's going on in this cell at all. We can just determine the probability to have any number of molecules in our gauge cell. So here we have a picture of the difference in incremental chemical potential between an adsorb and a free chain as a function of chain length. What we can see here is that for different adsorption potentials, which are the different colors, we have different behavior. For all chains, or for all cases where the adsorption potential is less than about 6, we have incremental chemical potential, which eventually becomes equal to that of our free chain. For anything which is stronger than that, we have increasingly constant potentials, which are increasingly more negative, which is what you'd expect, because we're adding more energy, or subtracting a similar amount of energy in each case, at each incremental step. We can also graph this CPA in the following manner. So this is our surface adsorption potential. This is normalized to a different value than we had in the previous figure. And this is the incremental chemical potential. These are for different chain lengths. And what we expect and what we find is that at the critical point, we have independence of the critical conditions on the chain length, denoted by the crossover of all the functions. And this crossover point points out where our critical adsorption potential is. So in order to prove that we have the critical conditions, I next looked at some more traditional methods for characterizing the critical conditions. What we show here is that as a function of our adsorption potential, the number of adsorbed monomers is a linear function of the adsorption potential up to a point, and that point is our critical condition, which is exactly the same as what I found for the incremental chemical potential case. I also looked at the radii of generation, which are basically, if you have a chain, you can determine what the perpendicular and parallel radii of generation are, and they scale with these things called the Fourier exponents, which are given by these equations. And again, this proves that we have in fact found the critical condition appropriately. So in summary, this first part of the work, I introduced a new method for assessing the critical point of adsorption of simple polymers adsorbing to surfaces. This was published in 2013 in a short communication. So I next, in the second to last piece of my dissertation, I applied what I just learned from the critical point of adsorption with incremental chemical potential to look at the chromatography of polymers on non-porous substrates. So a little bit of motivation here. What we want to be able to do is to separate colloidal-sized molecules, such as the polymers that we just talked about. And there are two main ways that we separate them, by their size or by their chemistry. One of the simplest ways to do this, and one of the most common, is called polymer chromatography, liquid polymer chromatography. So in liquid polymer chromatography, we take our mixed sample, which has a whole bunch of different chain lengths of polymers, and we inject it into something called a chromatographic column. Your chromatographic column is packed with spheres. In this case, I'm showing that they're not porous, but these spheres, the polymers interact differently with the spheres based on their size. So in one type of separation called entropic separation, the polymers are going to elute with the largest ones are going to elute first, because in size exclusion chromatography, your chains, you have good solvent conditions and your chains want to remain in solvent. This means that a very large chain can't feel all of the small nooks and crannies between your between your packing, as well as a really tiny chain can that can get into little pieces. And so the larger chains are going to elute prior to the smaller ones. Another kind of liquid chromatography is liquid absorption chromatography. In liquid absorption chromatography, your solvent is such that the chains want to stick to your stationary phase. In this case, small chains are going to elute before the larger chains, because a larger chain has a much higher probability that it's going to stick to something than a smaller one does. There's a third type of chromatography called critical conditions and gradient elution chromatography, which is one of the main aspects of this work, one of the main motivations for this work, I should say. So, there is a point at which, if we have isochromatic elution, which is one if we have a single solvent composition and all the same type of chemistry of polymer that are of different lengths, if we, at a certain solvent condition, we just get this big blob that all comes out all at once from the end of our column. And this is obviously not what we want. It's the complete opposite of what we want for a chromatographic separation. So in order to separate these chains, we have to, instead of separating them by their size, we need to separate them we can separate them by chemistry. And so one way to do this is by using gradient elution chromatography. In gradient elution chromatography, we change the concentration of one of the solvents over the length of your run, such that you can easily distinguish the critical points of each of these types of chains. So we can describe the elution of chains in a chromatographic column using something called the retention volume. The retention volume, VR, is the product of the speed at which the chains are flowing through the column, or the superficial velocity of the column, multiplied by the time at which we watch them exit the column. We can plot the retention volume as a function of chain length for different solvent compositions in a graph such as this one. So here we can see three different types of chromatography. The first one, which is shown by the purple and the blue, are size exclusion chromatography, which you can see by the largest chains eluting at a volume smaller than the smallest chains. On the other side, when at different solvent conditions, we have liquid absorption chromatography. In liquid absorption chromatography, your bigger chains are eluting much later than your smaller ones. And at the critical condition, we have chains which are eluting all at the same time. We describe our retention volume by this equation. VR equals the sum of two different parts, the volume of the liquid in the column and the volume of the solid. And the ratio between these two is called the partition coefficient. So the partition coefficient is indicative of the chromatographic regime that we're in. For the liquid absorption regime, the partition coefficient increases with chain length. For the size exclusion regime, your partition coefficient decreases with chain length. And at critical conditions, your partition coefficient is a constant. So the partition coefficient is related to the incremental chemical potential. And at critical conditions, we can show that the partition coefficient is equivalent to that same condition that we saw earlier, where the incremental chemical potential of absorbing free chains is equal. So in this section of the work, I expanded upon the previous section where I just looked at tether chains, and now I sample, because I want to sample the free energy of chains which are coming close to a surface. I tether chains at different distinct points away from the surface. I calculate their incremental chemical potentials, sum them up to get the free energy, and then calculate something which is the partition coefficient. In this case, the partition coefficient is called the Henry constant because we're only looking at absorption on a non-porous flat surface. And this is analogous to the Henry coefficient that we have in the simple fluids. This is a graph of the incremental chemical potential at the critical conditions. So what we see is that as the chain length increases, as a function of tethering distance, we have a constant in incremental chemical potential. This proves that we are again at critical conditions, except this time we're not tethering chains to the surface. We can also plot the Henry coefficient as a function of our absorption potential. And as we expect, at very weak absorption potential, or no absorption potential, the smallest chains have partition coefficients which are the smallest, and our Henry coefficient is the largest for our largest chains. At critical conditions, we have chain length independence of the partition coefficient, and at very large and at very strong absorption, we have the exact reverse. So I combined all this information on the partition coefficients, which I calculated using Monte Carlo simulations, into a macroscale retention model based on the assumption that we have spherical particles in our column packing. And with that, I was able to predict the different regimes of absorption using our absorption potential and compare them against the experimental solvent compositions. And what I was able to show is that with only, not exactly with no adjusted parameters, because we have one really, which is the absorption potential, but I was able to show that we can predict all three different types of chromatography using a Monte Carlo model. Now, the next thing that we want to do is to come up with some kind of correlation between your theoretical absorption strength and the real solvent composition. And so what I did was a simple linear interpolation to kind of plot this over the full range that I studied, with the critical conditions being at the center. So our critical conditions in this case corresponded to 0.54 in 7-nitrile and this 0.72 number in our absorption potential. So conclusions from this part of the work, I showed that critical conditions exist for non-porous substrates and can be described by the equality of incremental chemical potentials. I calculated thermodynamic partition coefficients for non-porous substrates and showed that with minimal parameterization, we have very excellent agreement with experimental measurements. This was published earlier this year in the Journal of Fluid and Interface Science. Okay, so in the final section, I extended the work of what I just did for non-porous surfaces to porous surfaces. So, like I just said, in the previous case, I only looked at the absorption of polymers on surfaces versus free chains. However, we now introduce the absorption of chains within pores. So these two additional cases here, complete absorption within pores, and also partial absorption within pores. So we have this thing called the flower conformation, with a root inside the pore and stem outside. So it's worth noting that in the experimental literature, we know that critical conditions exist on porous substrates. We know that critical conditions exist on porous substrates. However, there's been controversy in the theoretical literature about models of real chains on porous substrates, because people have shown that if you only consider the case of the partitioning of a chain that's completely confined versus one that's free, you don't have critical conditions anymore. They no longer exist. And this was an hypothesis first thing that I did to study this was to look at chains that are just confined to pores. And I did two different tests. In the first test, I looked at the incremental chemical potential of a chain at the external critical conditions, or so like at the critical conditions that we found for a chain on the solid surface, in pores of different sizes. And so the incremental chemical potential, as you can see, increases with chain length for all of the different pore sizes that I looked at. And the black line is the incremental chemical potential of free chain. And so what we found is that you only have the equality of incremental chemical potentials at a single chain length. What this proves is that you don't have critical conditions when, this would seem to indicate that you can't have critical conditions by just changing the pore size. The other thing that I did was to look at a single pore size in which the chains would normally fit the whole way and change the absorption potential to see if I could find a case where they would all intersect with this line. And again, you don't find that. The incremental chemical potential always increases because you're trying to pack more and more monomers into this small space. This can also be shown by the partition coefficient of chains between free space and confined pores, which is just the difference in the free energy of those two chain types. So what we see in both, this is the partition coefficient of chains confined to pore, which is 3 beads wide, and this is one which is 8 beads wide. And so what we see is that at no point is the partition coefficient constant. So this would seem to completely kill the case of having critical conditions on porous materials. However, we can introduce another mechanism that gives us another way to look at it. So, like I briefly talked about earlier, we can introduce the case of flower conformations. So, again, a flower conformation is a chain which is partially inside and partially outside of the pore space. And it's composed, the free energy of this chain is composed of two parts. A cis part, which is the external, and a trans part, which is inside the pore. The free energy of this type of chain is the sum of those two parts. This letter S is the degree of translocation of the chain, which is just the number of beads which are inside the chain, or inside the pore. So I next looked at the incremental chemical potential of chains which are in flower conformations over all degrees of translocation. And as you can see, this is the incremental chemical potential as a function, incremental chemical potential as a function of chain length. And what we can see is that at the same critical conditions that we have for external absorption on flat surfaces, we have critical conditions again. Likewise, if we look at partition coefficients, we have a crossover point for different chain lengths at the same value of critical conditions. Alternatively, we can look at partition coefficient as a function of chain length. And in this case, the red line shows us the Lewis constant. So I next took this information and employed a simple model substrate, which is shown here, on which to calculate retention volumes. So here we have our pores that are connected by these little cylindrical necks to a flat surface, and we have absorption both on the surface and in the pores. And using that retention model, I was able to compare my, so it's a little hard to see here in this picture, but I was able to compare the retention of a simple series of linear polystyrenes on a porous column in all three absorption regimes and showed critical retention. Furthermore, I used the relationship that I developed previously for the solvent composition versus the absorption potential to predict what the theoretical solvent composition would be based on my experimental or my theoretical predictions. And what I showed was that we actually large size exclusion regime. So, in summary of this last piece of the work, I showed that critical conditions exist for porous substrates and are equal to critical conditions on non-porous substrates. I showed that the thermodynamic partition coefficient can include three different mechanisms of absorption. Absorption on the external surface, complete and partial confinement. Furthermore, I showed that the theoretical results indicate a strong influence, or a tool, but anyway, this part of the work was, again, published very recently and was featured on the cover of College of Engineering Science. So, in summary, in part one, I developed a suite of analytical tools for determining the pore geometry and topology based on information from hysteresis and scanning groups. I developed DFT kernels for argon and CO2 absorption of microwave porous carbons. In the second part of my research, I present a new method for determining the critical point of absorption of polymers, and I apply this method to the chromatography of polymers and porous and non-porous substrates. With that, I would like to thank my doctoral advisor, Dr. Niemark, also my committee members, all of my industrial collaborators, my group members, my family and everybody for coming, and my funding resources. And with that, I'll take any of your questions. Thanks.
Okay, yeah, so thanks, Rich. So it was very comprehensive presentation, maybe too long. Right? So now please ask questions. So the only what I want to stress right now after listening to the presentation, that again, so the work is very diverse, and Rich during this time learned different methods, theoretical and computational, like percolation theory, to functional theory, Monte Carlo simulations, and what he did in his work, he applied the methods which are original, so it's not the methods which actually are available from other sources, but the methods which were developed here in the group and what he advanced. Okay, so having said this, so please open for discussion, ask any questions regarding the motivations, the conclusions, the outcomes of the research, and maybe some technical questions as well.
Yeah, when you look at the critical conditions, so
Can you speak up?
yeah, when you look at the critical conditions for non-porous surfaces, so what kind of geometry you consider, like bilateral? I mean, the surface geometry was.
Yeah, the surface was a plane
So
surface.
what happens if you have a curved surface, like porous and bilateral?
So in the case of it all depends on the complexity of your model, right? So in general, if you have a curved surface, it has a different interaction with the system. However, for the case of this, in this case, we use just a really simple square well potential that has the same interaction regardless of geometry. So we basically restrict ourselves to the case of this really simple case. If you had a curved geometry, you could introduce probably stronger interactions depending on the curvature. So in the case we have curving in, you probably has a little stronger, and if it's out, probably a little less than that. But this model is not meant to take care of that. It's meant to just look at the geometry and the very simple absorption interaction. Yes?
In your last work with the porous materials, you used several pores, right?
Sorry?
You used several pores?
No, so we actually,
One pore.
So we basically take one pore and extrapolate to a surface which has multiple pores.
I see.
So we only calculate the absorption in one pore, assuming that it's isolated from other pores. At the next level of complexity would be to have interactions with more than one.
I see. My question was gonna be if you had multiple pores, if you were considering to have a system with how would you call a my.
So
My
we're
terms just went
so
out
we're
the
actually thinking about trying to implement like a corrugated surface where you have multiple cylindrical pores instead of
Okay.
spherical pores. That and this is something we're trying to get a master's student for actually, or potentially I'll just do it this year.
All right. The word I was looking for is distribution.
Yeah.
Like, were you
Yeah.
considering to have a material that has like a variety of pore sizes, and then study this phenomenon?
That can also be done, also much more complicated.
I see.
Because once you have multiple pore sizes, you then have to decide how you're going to weigh them in your retention model. Yes.
You talk about size and chemistry exclusion of the polymers. But what happens if you have two polymers of similar chemistry and they're of similar size because one is technically more compact, let's say from being slightly cross-linked? Do you understand this situation? How would you distinguish?
So we only look at the case of polymers which are very, very dispersed. They're, we essentially are making the assumption in all of this work that we're in the dilute limit. So this is cross-linking. Well, okay, if there were very similar chains and like self-cross-linked, even so that was like
So the basic difference is density.
so in that case, if you had something where one of the chains was more compact than the other, then size excluded might be enough, depending on the situation.
They're similar in size because one has a shorter chain length.
Okay. Well, okay. So it would depend on. So what's your question exactly?
How would you differentiate between the two?
There's probably several different ways of doing this. If you're using size exclusion chromatography, I'm not 100% sure how. But you would probably end up with a difference in elution based on the fact that one is more of one shape and the other one is more free floating or more free.
Yeah.
Efim probably knows a whole lot more about that than I do. So
There's a ways to distinguish within these polymers because in absorption keys, interaction energy actually depends not on the size of molecules but number of monomer units. And obviously, cross-link polymer will have much higher molecular weight. It will have stronger absorption. So in this case, absorption chromatography will be, but also critical point probably will change. So it's ways, not size exclusions, other types of chromatography will be useful in this case.
Yeah, in your percolation model, basically, you would first show the agreement with experiment, then you go to characterization. But could you actually explain us what new, I would say, properties of material you exactly get in the characterization model? Because you flash some pore size distributions, right?
yes.
But so this pore size distribution, how are they different from a case when you don't really consider percolation explicitly?
Okay. So
or basically, do you have any like parameters which would describe general conductivity of force
yes.
from your strain method?
Yes. So this is a point that I excluded for brevity.
Okay.
But yeah.
So I think the questions from the committee should follow the questions from the audience.
Okay, because the audience basically had no more questions.
No, if audience no more questions, then the audience can applaud once again. And then we will have a close session.
That's a question from the back.
Yeah, so there was one question.
Yeah, just very simple, well, not too simple question, but brief. Is based on all the methodology that was developed here in the group. I don't know what is the status of this, but do you plan to like patent some of these ideas and maybe make your own business around this technology and stuff like this?
No, this should remain